Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over weak acid base equilibria. So let's get into this. What do we mean by a weak acid or a weak base? Well, in my previous video I talked about strong acids and strong bases, and I said that a strong acid and a strong base are those bases and acids that will dissociate or ionize completely in water. Basically, you don't have any of the molecule left. You don't really have any of the compound left. All you have are the ions. Well, for a weak acid and base, it's the opposite. So if you have a weak acid or a weak base, that means it's not going to be completely ionized in water. As a matter of fact, very, very little of it is going to actually ionize or dissociate in water. So that's what we mean by weak acid and weak base. So a tiny bit of your substance is actually going to be in the ion form. So the other thing to keep in mind is that because only a little bit actually dissociates, this is going to be a reversible process. So that means that we can use equilibrium constants, equilibrium expressions, ice tables, etc., to find pH values. So if we want to know what the pH of a certain concentration of a weak acid, we can use the equilibrium expressions, and we can use ice tables to figure that out just like we did before. So one of the things we want to remember is that K here is just a generic equilibrium constant, right? So that's what K stands for. It's an equilibrium constant. And then that equilibrium constant is given different names and different forms or symbols depending on what system you are looking at. Like, so for example, if we're looking at, say, a reaction that is happening at equilibrium and then we're using concentrations, then we call it Kc. If the species that we're looking at in the reversible reaction has gases in it and we want to use pressures, then it's called Kp. If we have, say, an equilibrium in the dissolving of a salt, right? So if we put a salt in water and maybe it dissolves a little bit, it'll form an equilibrium between the solid salt versus the aqueous ions that from the dissolved portion of that salt. And we would call that the KSP, the K solubility product constant, right? So we have the same thing for acids and bases. So if you have a weak acid, that's going to be at equilibrium between the unionized form and the ions that it releases or breaks into or ionizes into. So if we're dealing with an acid, if we're dealing with an equilibrium regarding the dissociation or ionization of an acid in water, then we call that the Ka, the equilibrium constant for the ionization of an acid in water. It's referred to as the acid ionization constant. But that's just a fancy word or fancy phrase of saying, oh, it's the equilibrium constant for an acid that's ionizing in water. And it's only a weak acid, so there's this equilibrium. The same thing for Kb. Kb is for bases, so this would be the ionization constant or the dissociation constant for a base in water. So this is also the equilibrium constant for a base, a weak base. So we call it Ka and Kb. So these are equilibrium constants, and because they're equilibrium constants, we can use things like ice tables, and we could set up the K expression of our acids and bases that are dissolved in water, the weak acids and bases dissolved in water, and we can then solve problems. And so for the equilibrium constants, the Ka and Kb, it's still products over reactants, the concentration of product over the concentration of reactants, which will be, in this case, for acids and bases, it's going to be the concentration of your dissociated or ionized ions over the concentration of your undissociated molecule or your compound that hasn't broken up into ions yet. So that's going to be the ratio that we're looking at. And so here's a few examples. So HA is usually what we use for the generic form or formula for a weak acid. So H is the hydrogen that comes off. A is your anion, A for anion. And so you'll see that the HA stays together and is in equilibrium with H plus and A minus. So this, if this is a weak acid, then most of our material, most of the substance in water is going to be in the molecular form. But some of it, a tiny bit, will be in the ionic form. So it would be the concentration of your A minus times the concentration of your H plus over the concentration of HA. And then you could say the same thing for your weak base. So you can have a weak base with a hydroxide ion in it. That's going to break apart into the hydroxide ion and the base that's left over, the base, the metal ion. Or you could have a base like ammonia reacting with water to form the BH plus and then leaving the OH minus from the water. Okay, so let's go ahead and go over a practice problem. Okay, so here's our practice problem. It's asking us to identify the acid, the base, conjugate acid, and conjugate base for the HC2H3O2, which is going to be abbreviated as HOAC. This is acetic acid. Then write the Ka expression. So here we have the balanced equation. So we need the balanced equation for our Ka expression. And so what we need to do then is to first identify acid base, conjugate base. So we look at these two for our acid and base. Remember, the acid and base is always going to be on the reactant side. Conjugate acid and base is always going to be on the product side. So we have to determine what's going to be the acid and base. So if we look over here, it looks like water picked up a hydrogen from the HC2H3O2 from the acetic acid. We see here that it's missing a hydrogen. So that means that this is the acid. And so water must be the base. Okay, so now we need to find the conjugate acid, conjugate base. So we look at the acid, we want to find the conjugate base of the acid. So remember, the difference between the acid and the conjugate base is just a proton. So whatever's left over after you remove the hydrogen, that's going to be our conjugate base. So that would be this right here. So this is going to be our conjugate base. And that means that this must be the conjugate acid. Because if we're going to go backwards, the H3O plus would donate a hydrogen, a proton, to the acetate ion here. And then we go back this way. We back with our acid and our base. So we've now labeled the acid base, conjugate base. So the next thing is to write our equilibrium expression. So since this is an acid reacting with water, that is going to be our Ka. So the Ka value, again, it's very important to understand what our Ka is. Ka and Kb are the dissociation or ionization constants or equilibrium constants for an acid or base in water. It's an expression of how the acid or base is interacting with water. So since we have an acid reacting with water as the base, then this is our Ka. So the equilibrium is going to be Ka. And so it's going to be Ka. Remember, it's going to be the concentration of the products over the concentration of the reactants. Notice that this is liquid water we're not going to include pure liquids in our expression. So the Ka expression ends up being H3O plus multiplied by, and then we're going to abbreviate this. We'll say this is OAC because we're saying that this is abbreviated HOAC, so it lost its hydrogen. And then on the bottom is the complete unionized acid. So that's going to be abbreviated HOAC. So that's the concentration of HOAC. And so this is the equilibrium concentration expression. This is the equilibrium expression for this acid in water. Okay, let's look more at Ka and Kb and talk about their sizes. Okay, let's talk about the size of our Ka and Kb. So let's look at first at the size of Ka for the weak acids. So we just did a practice problem involving acetic acid, and here's our Ka expression for that reaction with water. And so again, remember the Ka value of an acid is its reaction with water. That's what Ka is standing for. So here we see that the Ka value is 1.8 times 10 to the negative 5. That's very small, very much less than 1. So the question is, why is Ka so small? Well, a small Ka means that the equilibrium lies very far to the left. So it is favoring the reactants, meaning that at equilibrium, you're going to have much, much more reactant left than product. And the product, when we're talking about product of the acid, that's going to be the ions, the H plus and the anion that's ionized when you reach equilibrium. So basically, the the products here on the top are going to be very, very, very small, and then the reactant on the bottom is very large, so giving you a very small ratio. So again, that means it's reactant favored, meaning that very little of the acid is ionizing. Most of it stays together. And that makes sense because this is a weak acid. So weak acids are going to have Ka values less than 1 because they hardly dissociate. They're not going to form very much of the ion product, right? They're going to stay in this form, so therefore their Kas are going to be small. And then this leads to a low H plus concentration, and so your pHs for a weak acid are going to range from 2.0 to like 6.9, almost neutral pH, but not quite. So what about Kb? So the size of the Kb is for weak bases. And so here's the Kb expression, and here's a generic equation. And again, the Kb is defined as the equilibrium between the base and the water that it's reacting with. So here I have my generic base B, and here I have water. So the base is going to react with water. It's going to take a hydrogen, and then one of your products is going to be BH plus, and what's left over is OH minus. So for this generic reaction, your Kb expression is going to be the reactants, the concentration of your products over the concentration of your reactant, which is the base. We're ignoring water again because it's a liquid and we don't include liquids in our equilibrium expressions. So here's our equilibrium expression for a base, a weak base, and that we call that Kb. So weak bases have small Kb values for the same reasons that weak acids have small Ka values. right? So small kb means that the equilibrium lies to the left. They don't dissociate very much. So most of it is going to be in the form of reactant, not product. So your product is going to be very small. Your reactant is going to be very large, giving you a small ratio between these two. So we call that reactant favored. So there's not much dissociated. It is a weak base. So that indicates that you're going to have very little of this dissociated in water. And weak bases are going to have a Kb less than 1. So this is going to lead to a low pH, a low hydroxide ion concentration, and therefore the pH is going to range from 7.1 to 12. And so that is an explanation of the size of Ka and Kb. So let's go ahead and talk about the relationship between Ka, Kb, H plus concentration. Okay, so let's go over the relationship between Ka, the H plus concentration, pH, and Kb as far as acid and base strength go. So here I have a little chart here. So as you increase in acid strength, what's going to happen? So as acid strength increases, then Ka, which is a measure of the acid strength, because remember Ka is the ionization constant, the equilibrium constant of the ionization of an acid. So the stronger the acid, the more it's going to ionize, and therefore K is going to be larger. And that also means that your H plus concentration is going to be larger too, because more of it is ionizing. And since you're increasing the H plus concentration, that means your pH is going to decrease because it's the negative log of the H plus concentration. What about base strength? So as you increase the strength of the base, same thing applies. So your Kb, which is the equilibrium constant for the dissociation of a base in water, the more it dissociates, the stronger the base, the more it's going to dissociate, form those ions. And so that would make Kb larger because you're going to have more ions versus the base in its non-dissociated form. So Kb is going to be larger, and then that means the pH is going to be larger too, because more ions are going to dissociate, or more OH minus ions are going to be produced, and so that's going to lead to a higher pH. And so as the pH gets higher, more OH minus is produced. That means that the H3O plus or hydronium ion concentration is going to decrease, because remember that the pH and the OH are inverse to the H plus concentration. Okay, so let's go ahead and do a practice problem. Actually, I've changed my mind. I won't do a practice problem. I'll do a couple of practice problems, but not in this video. I'll do that for my next video. So that's it for this video. I hope this was helpful. If you found this helpful or interesting in any way, then please, by all means, like this video, hit that like button, and also make sure you subscribe to my channel. Hit that notification bell so you can be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. Thanks for joining me, and have a great day.